All right. So this looks like we are technically set up. Let's continue. Um, Gabriel will present us some code golf, and I was very excited because he actually in the submission, I think you just posted the one string that he will talk about now for 30 minutes. It's gonna be fun. And Gabriel is a first-time JuliaCon attendee. He gave his first talk this morning, so this is his second talk. Yeah, very excited to have new faces here.
Thank you.
Thank you.
All right, I'm Gabriel Konar-Steenberg. I'm a researcher at the National Renewable Energy Lab, but this is entirely unrelated to that. This is just a cool project I've done in my free time. So not to spoil the ending, but this is what we're going to be talking about. This is 70 characters of Julia. The new lines are just so it fits on the slide. And I have 43 slides to talk about 70 characters of Julia, and we'll see what we'll learn along the way. So taking a step back first, the goal here is we're looking for a program that calculates pi, although the number of digits it calculates is not important. So we're going to get up to 3.14159 and sometimes a 2. So like 6.5 digits. But the goal is to do that in a way that's explainable, both in the math and in the Julia tricks we took building upon that math, explainable to an 8th grader. And of course, we want to do so in as few characters as possible. And we'll learn along the way that optimizing for these goals lets us learn some cool computer science lessons along the way. Okay, so contents, we're going to start with the mathematical derivation of the pi algorithm we're using. We'll start with an initial non-golfed implementation and do this kind of mini golf through a bunch of CSE lessons, each of which will bring us closer to our goal of implementing this thing in 70 characters. We'll do a little bit of analysis of how well it works, and then there's some future work. So, first of all, our 8th grader might not understand the area of a circle, but we'll start with the definition. Pi is the ratio of a circle's diameter to its circumference. So we have this unit circle here with a diameter of 2. So its circumference is 2 pi. We're going to divide that up into a bunch of wedges. Here we have 8 wedges, so each wedge's arc length is 1/4 pi. We're going to rearrange those wedges into this strip. And our 8th grader doesn't know calculus, so we'll have to do a little bit of hand waving here, but we'll say that as we make those wedges smaller, the height of the thing is going to approach 1, which is the radius of our circle, and the length of the thing is going to approach pi. Add up all those arc lengths, half on one side and half on the other side. So the area of that rectangle that we've reformed our circle into is pi, so the area of our unit circle is pi. We're going to circumscribe a square around that. So that's a 2 by 2 square. So its area is going to be 4. And so if we generate a bunch of random points within the square, and the number of them within the circle is going to be proportional to the ratio of the areas between those two things. So it's going to be pi to 4, the number of dots within the circle versus the number of dots total within the square. If we do a little bit of algebra, rearrange that, we get our formula for pi. Pi is approximately 4 times the number of dots in the circle over the number of total dots. And again, this converges incredibly slowly, but that's not the point here. So here's our first implementation in Julia of this Monte Carlo pi algorithm. We keep track of the number of total dots, the number of dots in the circle. We generate random points between -1 and 1. We use the distance formula to figure out how far away they are from the origin. If they're less than 1 from the origin, that means they're within the circle, and we should increment our number of circle dots. And then we print out this ratio and loop forever. We're going to clean this up a little bit before we get to the golfing. First of all, we don't need the square root. Just square both sides of that. If the thing squared is less than 1, then the square root is less than 1. Also, we can define a little helper function for the random number rescaling. So there we go. It's already pretty short, but it's going to get quite a bit shorter. So most of the rest of this presentation will have what we have so far on the right. We'll have what we're doing right now on the left, and we'll have all the lessons we learned in the bottom right. Okay, so here's where we're starting. First of all, we can eliminate a branch. Oh, we switched from if else to this Julian short circuit thing, but it's still a branch. If you look at what this compiles to, there's a branch in there, and we don't need that. It turns out that true and false act like 1 and 0 in Julia, and so if the thing in the parentheses is true, it acts like a 1, and we can just add it like this to n. Branch elimination, here it's just a golfing thing. It can be useful for performance. Branches can be slow. It can be useful in like cryptography, where you want your algorithms to take the same amount of time no matter what the input is, so that no one can kind of try to attack you and figure out what your input is depending on what branches you took and how much time it took. So there are some uses for this. Here we're just using it because it's shorter. Okay, next lesson. We're doing 2 random number generations per iteration here for the x and y coordinates, picking a new x and y coordinate each time. We don't really need to do that. We can reuse one of the coordinates to do the next iteration and just re-randomize one of the coordinates at a time. Each one will get used twice, but we're still doing random points each time, and we're making more efficient use of those random numbers we're generating. So the way we're going to do that is we're just going to have x equal to the previous value of y. So pretty simple substitution there. We just have to define y globally. Yep. Okay. So no longer doing quite as much more work than we need to. Okay. Next, we have these 3 lines: x equals y equals random, and update. Those can all go on one line because in Julia assignments are expressions, so we can update the value of y and use the value of y at the same time. This is what this looks like. Basically, the first y squared is the previous value of y. The y equals my rand squared is updating y and also taking the new value of y squared. This works in Julia. In some variants of C, the compiler will complain about this. It doesn't like that y kind of has 2 different values in the same expression, but Julia lets us do this, and it's shorter, so we're going to. Okay, next. We've got these floating point values from -1 to 1. Floating point is kind of not the right thing to use here because we want to uniformly sample this space, so we should just use integers and rescale things to make that work. And that'll eventually unlock the door to some other golfing optimizations, but let's reparameterize this so we can use integers. First of all, we can multiply both sides of the inequality by 2. That doesn't change anything. Second of all, we can multiply by 2 within the squared thing if we multiply by 2 squared on the other side. So if we put it in a 2 there, the other thing becomes 4 times greater. That also doesn't change anything. And now we have the framework that we can use to go to integers. So we observe that the thing on the thing on the right-hand side of the inequality has a mathematical relationship to the thing within the y expression. And that's what this looks like. So if we have b, our square goes from -b to +b. So we're generating random numbers now, integers between -b and +b. And we just need to check the relationship to 2b squared. And this is algebraically equivalent, roughly. But now we're using integers. Okay. What next? Well, we can increase that integer, increase our resolution. Maybe our 8th grader has heard that powers of 2 are important in computer science. So we've got 2 to the power of 30. That's a pretty big number. It still works. Let's go higher. 2 to the power of 31. It doesn't work anymore. What has happened? We have discovered integer overflow is what has happened. So if we evaluate the expression on the right-hand side of that inequality there, it's supposed to be a really big number that we're comparing to, but it looks negative. So what's going on here? Well, I'll not try to explain all of base 2 to you guys, but the idea here is that our most significant bit actually represents a large negative power of 2. So when we try to make a number bigger and bigger, eventually that bit gets flipped and it becomes very negative, as this XKCD shows. So that's why we broke it. Basically, everything, none of these n's are going to be greater than this very negative number. So it's gonna converge to 0. Okay, but this also suggests a solution, because if the thing on the right is just on the boundary of overflowing, then the thing on the left that's supposed to be in the same range is also just on the boundary of overflowing. So rather than checking whether the thing on the left is less than a big number, we can check whether it has overflowed. We fixed it because now if the thing on the left is small, it'll be positive, and if the thing on the left we think should be big, it will have overflowed to be negative. So we've replaced comparison with a large number to opposite comparison with 0, and this works because the overflow happens in the exact right place. Okay, more data type stuff. We've got a 2 to the 31 there. Basically what's going on here is we're generating random 32-bit numbers. We're squaring them to make 64-bit numbers, and then we're doing some 64-bit comparisons. Well, we can just generate random 32-bit numbers and then make them 64-bit numbers. Now we don't have to have this B in here. It's longer for now, but it's cool that we can use data types in this way. Okay, we kind of don't like that rand in there. First of all, it's a bunch of characters. Rand in 32, that's too much space. Second of all, our goal is to be explainable, and I don't want to have to understand how the Soshiro algorithm works to generate random numbers. I don't want a dependency on that. So we open up Wikipedia, we find this simple random number generator called the linear congruential generator. We see some constants in there, and then we just kind of try stuff. We put non-constants in there, and we again, we're modding by the type rather than a number. And here we're kind of just trying stuff, but this particular stuff happens to work. So we generate a random number here, and we still have to assign extend to int64, but we'll be getting rid of that soon. Now we have our own random number generator that's very chaotic because it's like depending on lots of state here. It's kind of annoying that we can't like formally analyze what's going on there, or at least I haven't yet, but maybe that's some future work. Okay, what now? Well, now the biggest thing in here basically is these types. This type conversion to do the mod by 2 to the 31, and then extend back out to 64-bit integers. Now we have to teach our 8th grader about left shift and right shift. So if you have a number, a string of ones and zeros, left shift is gonna move it all to the left, basically padding with zeros at the least significant bits, and the most significant bits will overflow. And then if you arithmetic right shift it again, it'll bring things back, padding on the left this time. The one minor nuance here being that sign bit, again, we extend the 1 if it's a 1 and the 0 if it's a 0, so the sign doesn't do crazy stuff. And if you use these in concert, you can have a large number, only the least significant 32 bits of which you care about. You can shift it left to zero out all the higher significant stuff. That's probably not good randomness. And then shift it back to the right, and now you've zeroed out or one'd out as appropriate all the higher significant bits, and you've got an int64 filled with a random int32. So that's what that looks like. We're just replacing the casting with shifts. But now it looks like we have another parameter here. We have two 32s. Do they both need to be 32? Would it be better to kind of sample from the middle of this 64-ish bit random-ish thing we've generated? Again, we're going to get kind of empirical here. There are RNG tests. This is an old one called Die Harder. I ran it a while ago on the C implementation of this, and you can try different left shifts here and see what tends to pass more of the tests, which is again kind of unsatisfying, but future work, I guess. And it turns out that 25 is nice. This isn't real output, this is example output, but 25 tended to give better performance on the random number generator test. And it actually gives pretty good performance, which is cool because we kind of just made up this random number generator without doing much analysis of it. Okay, so 25 there then. What next? We're kind of defining a lot of variables, and that's taking up space. Let's use a for loop. We'll just put a really big number there for now. That'll get better. But now we don't have to define t. All right, we still have to define n and y, though. What can we do about that? Operators in Julia are functions, and functions you can add more methods to. And functions also give you variables from their arguments to work with, and then you don't have to set them equal to something at the beginning. You can just call the function. Okay, so the backslash operator in Julia, we're gonna redefine it to be this algorithm. And then we pass in to the backslash operator the things that we want to initialize n and y to. So here, instead of n equals y equals 1, we're passing in 5 and 27 to this backslash function. And then we'll start out with n equals 5 and y equals 27. And this lets us shave a few bytes off. Okay. We're almost there. This is what we have so far. We've got a big number in there, which is annoying, but most of the rest of it looks like the final thing. We chose 5 and 27 for a reason, and that's that 5 to the 27 is almost the biggest number we can represent within 64s. So rather than t up to a big number, we do t up to n to the y, which is a big number, and it's shorter. And then the only thing we have to do is mess around with the white space a little bit, and we're there. So we have this backslash function that initializes n and y to 5 and 27. We have a loop of t from a small number to a big number. We're doing that same Monte Carlo thing where we have the previous y becomes the x, the new y from our custom random number generator using that linear congruential thing and some bit twiddling. We compare that to whether it's within the circle or not using integer overflow, and then we print out the answer. Okay. Might as well see how fast this is, even though it only gets us 6 digits of pi. So the C implementation, compiled with GCC told to optimize, runs about 17 billion iterations in 50 seconds, which sounds fast. But if you look at the assembly this is generating, it's using the stack. It's not keeping everything within registers. And I guess we've moved a little bit beyond what our 8th grader knows about, but there's different parts of a computer's memory, different memory locations, and certain ones are like right on the CPU, and those are really fast. And there's just a few of them, but there's not much going on here. We can get away with just those. So we can write our own assembly and get it down to 46 seconds. It turns out the Julia program seems to run in 45 seconds, which I don't have statistical significance here. I don't know. I haven't looked at the Julia emitted assembly, but this is kind of cool. It's weird and cool that we can get faster than GCC using Julia. Just to recap, we derived an algorithm for computing pi. We wrote a program to implement that algorithm, and then we did a bunch of tricks using a bunch of CS knowledge to make it really short. And it runs kind of fast, but also it converges super slowly. There's a lot of things that could still be done here to teach us even more. Can we more formally analyze what's going on with that random number generator? Can we get better on Die Hard or a more modern test suite? What's going on with the compilers? Why is GCC not eliminating the stack references here? What would happen if we tried to parallelize this? Can we run this on a GPU? So I invite you, if you'd like to continue learning with the 70-character Monte Carlo pi algorithm. I've been Gabriel Konar-Steenberg. That's my website. You can find this in several languages on the website. Happy to take questions.
Do we have questions from the audience? Yes.
Thanks. Great talk. I really love like stepping through all that. This is great. Sort of a question about the algorithm you use. What limits the rate of convergence here? Or do you have any intuition around what limits the rate of convergence?
I mean, there's a fundamental limit around, like, if you sampled every single point
Mhm.
in the whole square, like int64 by int64,
Mhm.
you'd still only not get that many digits. So that's really, I think, the hard limit.
Okay. So did you try this? I mean, you lose the code golf aspect of this, but did you try this with like int16 or int32 and see how the precision compares?
I had an int32 version initially, and it was worse, but
Okay.
unfortunately, I don't remember how
Okay.
much worse.
Cool.
Do you have more questions? So I have a question. What made you choose this particular problem, and what? So if I would like to play my own game of code golf, what are the characteristics of a algorithm or a problem that might be particularly suitable to play around in this sense?
I think different people do this in different ways. I like this one because it's small enough and tractable enough that you can feel like you're able to really spend a ton of time on each bit of it, like multiple minutes or multiple hours per character. And I think that's kind of cool, but certainly most code golf things are longer than this. But I found that aspect cool, and I've also found the explainability and the teachability cool. I guess I wasn't expecting to be able to use this many CSE tricks to do this, and so that aspect has been cool, and so that's kept me going on this one.
Are there tricks that you still have up your sleeve that you have not been able to push into this particular problem?
Yeah, sometimes at night I stare at this thing and I think of where the like most ordered bits are. Where does it look like there's slop in there that could have a greater entropy? And the left and right shifting looks long to me, and the print line looks long. Like, I think you can get a little shorter with at show, but those, I mean, more interestingly, the first one. I wonder if there's a better way to do that, but I've worked at it for a while and I haven't found one. So if anyone does, email me.
Versus 27 and 25. What if you just bit shifted by y?
Say again?
How much worse? Oh no, I guess the y is going to change every loop though. Never mind.
So yeah, this 25 isn't that important. It can be 32 and it still works. It cannot be a single digit number and still work, unfortunately. And oh yeah, the 27. Yes, the 27 could be less. It just seems annoying that the thing would then have to stop before it explored the whole space.
Hey there, was there a particular reason you used a backslash operator outside of convenience? Because, like, that's, I guess, technically site piracy, but
Yeah, it's super bad. I could have used, let's see, I'm using plus, so I couldn't use that. I could have used like forward division, make it even worse. Um, I mean, the reason is that it's a single character and it's not a special character. I was trying ideally to avoid special characters. Um, I think there might be some special character operators that don't have default implementations, and so it would be less bad to use those. Um, but yeah, just a stylistic choice.
So if there are no more questions in this audience, it feels like we were just given our own private little version of a computer file video, and I'm very thankful for it. So yeah, let's thank the speaker again.
Thanks.